In this problem, we are going to be looking at a high-pass filter. This can be found in the notes linked below the like button, dealing with section 14.3. On page 111, we know that the omega c is, we can use this to find our cutoff frequency. And we can use this to find our cutoff frequency because we know that frequency is tied to our omega. Well, omega is equal to 2 pi times f. So we can rewrite this as our f of c is equal to omega c divided by 2 pi. And so that's going to be our frequency. Now we need to find our omega c. And again, this is in the notes, but our omega c is equal to 1 over our r times c. So let's plug some things in. We know that our R is 25 nanofarads, so this is 25 times 10 to the negative 9. And our resistor is 50 kilo ohms, and this is 50 times 10 to the cubed. And this is both going to be divided by 1. This is going to give us approximately 800 for our omega. So we can write here that omega c is equal to 800. Now we need to plug this in to our omega c here, that way we can get our frequency. So we're going to have 800 divided by 2, which is also divided by pi, and then for our f of c, we are going to get approximately 127 hertz. For the following answers in polar form, we need to write the answers with a positive magnitude and the smallest appropriate positive angle. What this is basically saying is we need to find our h of s, and then we need to plug j omega into it, and then we need to solve using this. So let's actually go ahead and find our h of s. Our h of s we know is equal to v naught over v input. And we can find v naught over v input of the circuit by using the voltage divider method. So we have the voltage equal to the source voltage. And then we have the impedance tied to that voltage. So we have this resistor for this problem. And then in the denominator, we are going to have that same impedance plus whatever other impedance we have on this side. Here we just have a capacitor. Now we are dealing in the S domain. So we are going to need to convert this dc to be 1 over s times c. So when we plug this in here, we're going to have 1 over s times c. We're going to multiply both sides by v naught over vi. So that will give us our h of s. And then we are going to multiply all of this by sc over sc to get rid of the denominator right there. And so we consider h of s equal to r times sc divided by r times sc plus 1. And that will be our h of s. Now we can substitute a j omega in for our s, and this is going to give us r times c times j omega, all divided by r times c times j omega plus 1. And so essentially we have our real number right here. I'll just call this real. And then we have an imaginary number right here. And then we just have an imaginary number here. And then we can say plus 0 is our real number here. Now we don't need to solve for this specifically yet. We just need this general equation. Because what we are going to do is we are going to take this j omega equal to 0.2 times our omega c and plug it into here. So for this first one, we're going to have h times the 0.2 times our omega c, which is 800. And this is equal to all of this. So we're going to have r times c times our omega times j. And then when I plug this into my calculator, I'm going to represent it as I instead of j. Our omega is 800. This is divided by our r times c times our I times 800 plus 1. Now, this is going to differ for every single problem. Remember that. That's super important. And that's because, or for these problems, by the way, because we can see that they equal two different things. But if we plug this part into a calculator with the 0.2, we should get 1 over 26 plus I, or j, times 5 divided by 26. And so that is the rectangular form for it, the complex form. We're going to need it in polar form. To have this in polar form, we're going to use that our Vmax is equal to the square root of our imaginary number squared plus our real number squared. And then our tangent -1 is our imaginary number over our real number. And so that is how we would find that. And if we put the rectangular form into the polar form, you're going to get 0.196 at an angle of 79 degrees. Now, for this next one, we are going to have something similar, but instead of 0.2 times 800, we're just going to have 800. Because we can see inside of here, it's just j omega equal to j omega c. We don't have the 0.2 in here. So when we plug this in, it's just going to look like this. And I actually made a mistake. This 0.2 right here should be being multiplied in right here. So it should be 800 times 0.2 for both of those. And that will give us this. I made a slight error right there. So when we're looking at this, and I'll actually do it on a calculator, we have I times 800 times 0.2 here, and then times 0.2 here. And then if I were to click go, we can see with the 0.2 in here, it's 1 over 26 plus I, 5 divided by 26, which is 1 over 26 plus 5 divided by 26. So that's how that would look. Now, if we were to plug this 800 in here, we would not be using these 0.2s. So just plugging 800 in here, I'm going to get rid of these 0.2s I just put in, click go, and then we're going to get 1/2 plus j times 1/2. So this is equal to 1/2 plus j 1/2. Now we need to convert this rectangular form into the polar form using these equations, and we're going to get 0.71 at an angle of 45 degrees. Now we're going to do the same thing for the last one. We're going to plug it into our general equation, but we're just going to multiply this by 5 and this by 5, click go, and then we can see it'll give us a 25 over 26 plus j times 5 divided by 26. And then we need to convert this rectangular form into the actual polar form for it. Again, using these equations right here, we are going to get 0.981 at an angle of 11.3 degrees. And that is how you'd go about solving for this problem. We would have to use a calculator. I mean, we wouldn't have to, but it would give us a pretty big number if we didn't. And it's pretty simple. You would just follow these steps. First, you would find the omega c, and then use that to find the frequency, and then you'd find the voltage divider up here. You'd go down, you'd come here, make a general equation. General equation is super important. You want to stop at the general equation, and then you want to plug in these values right here. Remember, I didn't write it for the gray, but for the gray we would have h, and then we would have 5 times 800, like this. And we would plug into here. Just because I made a mistake I'm going to rewrite it. So we have h 5 times 800, and this would be equal to our general equation, so RC, but we're going to have j, or I, whatever have you, 5 times 800, and this is divided by RC, j times 5 times 800, and then we have our plus 1. And so that is the general equation for it, and that's how you go about solving this problem.